Hey guys, let's talk about kinematic equations, okay? I know this was not a lot of you guys' favorite thing last year, but hopefully we can make them a little less painless this year, all right? So kinematic equations, those are those equations that describe motion, mostly in one dimension. When we get to projectiles, then we will tweak our kinematic equations a little bit to work in two different dimensions, okay? But today we're just going to talk about the kinematic equations themselves. So these are on that equation chart we were just on, so I'm not going to take a super lot of your time. This means V average, okay? So if you put that little bar over the top, it means an average. You can find your average velocity by just looking at your overall displacement over your overall time interval, okay? Displacement can be found by taking your final minus the initial. So for those of you who were not in AP Physics last year, this little zero thing right here, think of it as a zero, meaning at time equals zero, okay? It's pronounced not, so X naught. If you're more comfortable using the I and F for initial and final, you can do that as well, okay? So if you use those, it's always your final minus your initial. Oh my gosh, I can't write today, okay? You can, either way is fine. All right, we can then break this equation down, rearrange it for position. And there's our equation for position. This is also the mathematical model for a position time graph. And remember, mathematical model is just a fancy word for equation of the line. Okay, this is rearranged a little bit. This is your Y, this is your MX, and this is your B. So think about that initial position as your Y intercept. I should have said plus, not equals. Okay, so that's average velocity. Instantaneous velocity is going to be a little bit different, okay? So instantaneous is just a fancy word for right now. So in instantaneous velocity, think of that as taking a photograph. Average velocity is more like taking a video, okay? So that's a good way to think of it. So now in AP Physics C, we need to do derivatives to find instantaneous velocity. So this would definitely be on a curved graph because if this was a constant velocity position time graph, then we would just take the slope of the line because it has the same velocity the average velocity the whole time. So we need to do the derivative when we have position graphs that look like that, or a position graph that looks like that, or any of those combinations when we talked about things accelerating. So we refer to velocity as being the derivative of the position with respect to time. And we're going to do a little bit with derivatives in a moment, but just for now, we're going to leave it there. Okay, so this is your instantaneous velocity. Notice there are no subscripts on your velocity. That means they're talking about an instantaneous. If it says V average or it has a bar over it, they're talking about an average velocity. Okay. All right, average acceleration. So again, this is the average over the whole time interval. So you would look at your change in velocity over the whole time interval divided by your change in time. Well, the change in velocity is the final velocity minus the initial velocity divided by the time interval. And we can rewrite that as the final velocity is the initial velocity plus your average acceleration times time. So again, this is your Y equals mx plus b. They just have the mx and the b reversed. So again, think of that initial velocity as your y-intercept, okay? Because y is what you're going to graph on the y-axis. Velocity is what you're going to graph on the y-axis, all right? So this is your mathematical model for an a velocity time graph, okay? All right, instantaneous acceleration. Again, instantaneous, just a fancy word for right now. Instantaneous, let's see if I can spell. So again, a picture versus a video. So average is a video, instantaneous is right now or a picture. Okay, so instantaneous acceleration. Now we are going to talk about it as being the derivative of velocity with respect to time. Okay? And we will talk some more about that in a minute. But I don't want to bog you down with a bunch of calculus just right now. So we need to do derivatives for the instantaneous acceleration. Again, think of it as a graph of velocity versus time, and we have a curve, which we won't really see in here, but you will see equations for non-constant acceleration, okay? But you won't be calculating things other than derivatives for that, okay? All right, so I've showed you so far now 2 of the 3 kinematic equations that are on your equation chart. That's one of them. The one we did over here is one of them. So let's talk about the third one, okay? The third one is the position is equal to the initial position plus the initial velocity times time plus 1/2 AT squared. Okay, this is your third kinematic equation. This comes from a graph. It also comes from integrating. We're not going to talk about integration yet, but when we get there, I will show that to you. For those of you who are in Calculus 3, you'll know what I'm talking about with the integration. We can talk about that now. But for everybody else, we're just going to worry about derivatives, okay? So let's talk about that. So when we do a graph, so we have a velocity time graph, okay? And we have our initial velocity here. These are all going to be positive velocities. And we have some velocity going on here, okay? Well, to find displacement, we would be looking at area, okay? So the area is equal to the displacement. So area is equal to the displacement. When we talk about integrating, areas will be our integral, okay? Slope, on the other hand, the slope of this graph would give you acceleration, okay? But slopes we define as a rate of change. And when we do the calculus here, we will be doing derivatives when we talk about taking slopes, okay? So let's look at the area under this graph since that's our displacement. Oh, my pen does not want to write. Okay, displacement is area under the graph, okay? You may see it listed as area under the curve in some instances. They really mean between the line and the x-axis. So like as I drew it here, okay? So let me use a different color. We have our time t down here. So if I look at this, this is a rectangle with a height of v naught and a base of t. So the area here is v naught t, okay? If I look at this triangle up here, then it has a height of v minus v naught. It has a base of t, and then it's a triangle, so I have to divide that whole thing by 2, okay? So if my displacement is area under the curve, then my displacement is the same as the initial velocity times time plus 1/2 of v minus v naught t, okay? Well, we have, we can add these together, do like denominators. Remember doing that a long time ago. So we really end up with 2 over 2 here, so we can match our denominator here. And when we do that math, we actually get 1/2 v plus v naught t. Oops, that should be in parentheses, not the other part. It's almost time for class, so I'm trying to hurry. Sorry. All right. Let me erase some of this down here because we don't need it right now. I'm going to erase that right there. Okay. So going back over here, all right, we have, this is, we are going to take this and we're going to look at this equation. Okay, and so we can rewrite this now as v naught t plus 1/2 of AT times the time, okay? We're getting that from there, and we ultimately get our equation for displacement, which is v naught t plus 1/2 AT squared. Okay, that's how you get it from the graph. Am I expecting you to be able to do that right away? Of course not. We will get there eventually though. But you'll notice that this equation here is the same as this one. We just took that and made it our change in x, because change in x is equal to the final minus the initial, okay? All right, so let's talk about how we're going to simplify that a little bit for AP Physics C. And yes, this will be easier. Instead of taking all these areas, we're going to do derivatives, okay? So right now, I'm going to take this kinematic equation, and we're going to talk about taking the derivative, okay? So when you take the derivative of something, you, let me see what never mind. We're not taking derivatives yet. We're still deriving equations. I'm getting ahead of myself. All right, so we're going to substitute some other equations in here. All right, so we can rearrange equation 2, which was this one, and solve it for V naught. So if I solve it for V naught, I'm solving it for T. We're going to solve it for T. So solving for T, I have to subtract this from both sides, and then I have to divide by the acceleration. So looks just like our average acceleration equation. So I'm going to plug that in over here for this T. So V minus V naught, not equals, it should be a minus. V minus V naught over the acceleration plus 1/2 A. And now we're plugging it back in here to V minus V naught over A squared. So we plugged it in for this T as well, okay? So we took that from equation 2, which we solved for T. So now I'm going to multiply through by acceleration to move that out of there. So I have acceleration. I'm going to move this over as well. So now I have it equal to V minus V naught squared. Oh, I do not know why this wants to keep. Plus 1/2 of V squared minus 1/2. And you get 2V V naught plus 1/2 V naught squared. Okay, so I have a 2 that reduces here. So on my next line, I end up with, I have 1/2 V squared minus 1/2 V naught squared is equal to this. I'm going to erase this down here to get it out of my way because we don't need it anymore. And I ultimately get this equation. If I multiply both sides by 2, so my 1/2s go away, and then I added the V naught to both sides to finally get equation number 3. Okay, so I showed you where to get equation number 1. I showed you where to get equation number 3. Okay, this was equation 3. Equation 3 and equation 1. Is that what I did? I don't know. Now I'm confusing myself. Hopefully I'm not confusing you guys too much. All right, so that's how you get those 3 kinematic equations. I'm going to leave it there for now because the video is getting longer than I wanted it to be, and I will talk about taking derivatives in the next video. Talk to you guys later.